All right. So in the last class, we were looking at low-pass filters, and we were discussing the idea that we can try to fix up our filter's frequency or the so-called cutoff frequency at a point such that we are able to separate out the wave frequency components and the low frequency components. And we are looking at how we can do this using first order filters. And the main idea here was that we choose this cutoff frequency in such a way that we can eliminate all the wave frequencies to the right of it. And that is quite possible to do as long as we have a good amount of separation between the control bandwidth of the system and as well as the wave frequencies being separated out sufficiently. So then you can choose appropriately a cutoff frequency in between so that this can be achieved. But we also understood the problem that in case that is not the case, it may be a little more complex. So we have to deal with what happens if the control bandwidth is actually longer or bigger than what the wave frequency regime looks like. So let's say that if the control bandwidth was up till here, but the wave frequency spectrum ranges somewhere here, then what do? In that case, you are in trouble because you can't effectively choose a point and say that I'll try to filter off everything beyond of that. Right? So the idea there would be that we'll use something called as notch filters. So I'll try to tell you what is the main concept. So we'll say that this is a band, or let's say this is a band in which I want to reduce the so-called gain value of my filtered response so that it kind of reduces in that wave frequency region, but it's like a band pass filter. Okay. So in the main, wherever is the main peak of the wave frequency spectrum, around that I want it to be a little less. And then after a point, after I exceed the control bandwidth, I should have a low pass filtering effect. So the low pass filtering effect continues to be there after I cross my control bandwidth. But inside the control bandwidth, since it is intersecting now with my wave frequency regime, I want to make sure that that wave frequency regime is kind of subdued somewhat. Okay, so what we'll here use is we'll use the cascade of two filters. We'll use our regular low pass filter, which will taper off everything beyond the control bandwidth, but we also need something inside the control bandwidth to take care of the wave elevation effects. So the idea is we'll use this so-called concept of notch filters and wave low pass filters put in cascaded. So which means that we have our estimated value of the heading angle is given by cascade of the low pass filter, cascaded by the notch filter, cascaded by the output from the compass, which contains the complete signal. Now, this notch filter looks something like this. So the transfer function for this notch filter looks something like this. You'll see that the bottom is s plus omega n square and the top is s square plus 2 zeta omega n s plus omega n square. So it is as if it is trying to take a comparison between a so-called critically damped system and a non-critically damped system. It's kind of taking a response of that. The reason, what will happen is basically when I put these two together, the notch filter and the low pass filter, you'll see something like this come out of it. So let's see what happens. So when we have this zeta value specified as 0.1, so the damping is low, then you will see that this thing is barely making a dent here. Correct? Now, as I keep increasing zeta, you will see that the effect of this filter is that in a particular band around the frequency of interest to us, it's basically reducing the gain value. Okay, and I'm plotting the gain here in decibels. Okay, what that means is 20 log of the whatever is the transfer function. Okay. So the idea here then becomes that I'm trying to filter out frequencies around the interest of wave frequencies. So typically I would like to choose where is the peak of the spectrum, where the maximum energy is located. At that frequency around that, I want to make sure that this must be reduced a little bit. Now, sometimes what happens is we may need a bigger bandwidth. So our frequency, so especially if you're considering in the low C states, then you'll see that your spectrum is a little more spread out. As you go to higher C states, if you ever observe the John Swab spectrum, try to see if I can move the page here. So if you have seen the John Swab spectrum or PM spectrum, it looks something like that, right? Once I start looking at lower C states, which means the significant wave height is a little lower, then you'll see that these, if the spectrum's peak is supposed to be at the same location, it will look something like that. So what is happening? At lower C states or lower wave heights, the spectrum is more flatter. So the peak is not so eminent. Is everybody following me there? It's kind of the frequency of, there's a range of frequencies where the energy is concentrated. So that the peak itself is not as representative as in the case of higher C states. In the higher C states, you can clearly see that the much of the energy is actually dominated in this region. So in that case, you can naturally pick up a notch filter with one frequency point, which is aligning with the peak frequency of the waves. Then your job is done. But if you're looking at a lower C states, you might want to eliminate a much broader range of frequencies. So in which case, what we do is we cascade multiple notch filters, one next to the other. Okay, and that's what you see as the this picture which you see, this curve. That is 3 cascaded notch filters with each having its own frequencies. So you see that the first frequency is here, second one here, third one here. So I'm trying to extend the range of the notch filtering effect by making sure that multiple filters with different frequencies are put together so that over a broad range of frequencies, I can avoid the necessary wave frequency effects can be filtered out. Okay, again, as before, you will see that it does have an effect on the phase, that as you start increasing the damping values in your filter, zeta values, you will see that the phase changes much more. Without the damping values being close to 0, you will see that the phase is almost close to 0, which means there is no delay in the system. But as you keep on adding more and more, the damping is increased. So you're kind of trying to actively filter out these responses from the wave frequency regime. You will see that you're also incurring it at a cost. So it's not coming free of cost. The cost is actually coming in terms of the phase lag. And we saw that the phase lag was in one direction only when we looked at the low pass filters. But here you will see that the phase lag is opposite on 2 different effects. So which means that frequencies which are less than the notch frequency are having a phase lag, but frequency components which are to the right of the phase and notch frequency are seeing a phase forward. The shift is in the opposite direction. Sensing that that was not the case when we looked at the low pass filters. The phase was always lagging there. Whereas when we are doing the notch filtering, that's not always the case. The phase may lag in some frequencies and the phase may go forward in some more frequencies, which may result in a signal which you get back, which may not be looking anywhere close to what you were beginning to think about. There can be effects which might be problematic. But as long as they are all attributed to wave frequency effects, it doesn't make much of a difference, because even though, let's say, these components have very large phase differences, the effective amplitudes are much smaller. Okay. And our interest is that the low frequency stuff which we really want to compensate for can be effectively be compensated without much phase difference. So again, as a control engineer, you have to play around with these damping values in your filters in order to make sure that an effective you can effectively eliminate some of the frequencies of interest, and you can keep the frequencies of interest and eliminate the ones which you do not want. Okay. I hope that's making sense. Yes. So far what we have looked at is the idea that if we have a compass measurement which contains both low frequency and wave frequency based signals, how to eliminate or how to separate out the components which are coming from the low frequency so that those can be used back in our feedback systems. That's the main idea. Okay. All right. Now, one of the key aspects which you might wonder is this so-called encounter wave frequency, this omega E, which I want to match with my notch filter's frequency. How do I estimate that? Generally, we don't know the environment when we are operating in the field. We may not know precisely what is the peak period, what is the, in simulations we'll know them perfectly, but in the field we may not know them perfectly. So in which case, how do we go about estimating what is the actual encounter frequency which I should compensate for, right? The idea there becomes that you can look at the motions of the vessel from your sensors and then try to estimate where that encounter frequency is. Now, usually if it's a single sinusoid, it is fairly easy to find it out. But if it is generally a spectrum composed with some more things, you may have a little bit of a tough time to figure out where the natural frequency or the peak frequency of the spectrum is. Usually people will try to either go with heave or pitch motions in order to figure out where the peak frequency of the spectrum is happening. That will give you a good amount estimate. So in essence, what we will be doing there is, as long as we assume that the environment is not significantly changing with time, which means that the environment is incident in only one direction, right? So assuming that the speed of the ship is constant in one direction, it's not changing rapidly with time, and the direction of the waves or the direction of the wind or the direction of the current is more or less constant for at least 30 to 40 minutes, then we can make a good amount of estimate based on the fact that we simply collect the information in heave or pitch, take a Fourier transform of it, and we'll know where the peak is. But in case if my environment is changing with time, so let's say the wave direction is changing with time or the wind direction is changing with time, then you are in trouble. You do not know where that peak will be because the encounter frequency will keep changing now. In which case you might want to go for an observer in order to figure out where that is. You may have to build a nonlinear observer. But for most practical purposes, Cs don't change that drastically. So for most of our applications, for 30 minutes or so, if you're looking at a dynamic positioning application, you can get away with the fact that the environment doesn't change that rapidly. So you can collect some information for a while, and then based on that, figure out what is the encounter frequency of the waves which are coming in, by simply taking a fast Fourier transform and finding out where the peak of that Fourier transform is occurring. Okay, and that will tell you where to place my notch filter's frequency so that I can eliminate the frequencies around it so that I can get a filtered response out, even in the case where the control bandwidth is exceeding the wave frequency or there is an overlap between the control bandwidth and the wave frequency regime. Is that making sense? Yes, no? Any questions so far?
Sir, can you explain again how to find the encounter frequency using
the encounter frequency? That is pretty straightforward. Let's say that I have a time history, right? So I'm simply measuring, let us say, heave acceleration. I can get this from an IMU or something like an IMU mounted on board a vessel, right? I can figure out how the heave acceleration is varying with time. I'll get some time history. Okay, my drawing is not very good, excuse that, but let's assume that we have a good amount of time history. We simply take a fast Fourier transform of this, and then you convert it into the frequency domain, basically. And you'll see that in the frequency domain, something like that might come out. Okay, so you basically see where the peak of this thing is, and that becomes your encounter frequency that you need to deal with. Now you choose your notch filters frequency as equal to the encounter frequency so that you can filter out frequencies around this notch filter and then effectively eliminate the wave components which have significant energy. Okay? All right. Any other queries?
So from the FFT graph, we actually get the response, like which frequencies the ship actually responds really highly. That is actually in this case omega E, right? But that also depends on the RA of the ship, right?
No, this is measurement, right? This is measurement from your heave.
Yeah, that is actually output that the heave gives with respect to like a input of a wave. So that's basically like RAO times the wave elevation.
Yeah, I don't care about the amplitude. No, I'm only interested in finding out the frequency. So the wave will also be of the same encounter frequency as the response is, right?
But that will be actually a product of the RAO as well as the.
Correct. That's right. In fact, this will be omega square times the product of the RAO times the wave amplitude. But I don't really care about the amplitude.
Okay, yeah,
I'm just interested in where the peak is,
yes.
So that I can get the. I can just get the encounter frequency out of it.
Yeah, I think I got it. Yeah.
Right. In fact, if you are so concerned about the frequency, you can divide by frequency and then take it as divide by omega square and then take the peak.
Yeah.
That also can be done. Right? But that's the traditional way that it is done, in the sense that you get a time signal, you collect some data for a while, and then identify where the peak of the spectrum is, and then that tells you that is the range of wave frequencies which I need to eliminate. Okay, everybody with me so far? So that once I do that elimination, whatever is the output left, that can be now given as a feedback to my control system, which can then try to compensate for those disturbances which are coming in. Okay, so this is the basic idea which you will see for a long time. Mostly this is how it was implemented back in the day. Okay, low pass filters, cascading, notch filters and other things were what were used. And many times until the coming up of the digital computers, many times this was done using analog filters. So they were trying out different approaches to do this. But with the advent of digital computers, now mostly you'll see that this is done digitally. Okay. So, but with the advent of the so-called 1960s, when Kalman filter came around, near about that time, a different types of observers started being built, where we could make a precise estimate of what this low frequency component is, better than just trying to cut off a certain frequencies and believe that whatever has been cut off is good enough for us. So can we do anything better than that was the question. And a few types of observers started to be built, which could estimate this low frequencies component and isolate it and give it to you. So we'll look at a few of them, which will eventually lead us into what is called as the Kalman filter. Okay. So the first one which we'll discuss is called the fixed gain observers. So these are simple state estimators and they can reconstruct the unmeasured state vector of the vessel from the control inputs and the measurements of a dynamical system. Which means that let us say that you are looking at the heading control problem, then the idea is that if I only know the measurement, let's say I'm only looking at a compass measurement, okay, so I know what is the yaw angle, and I know what is the rudder angles that I'm applying over a certain time, can I estimate what is the full state vector of my vessel? Which in this case, we can say that it is what is the yaw rate, what is the yaw angle. Can I precisely figure out, and can I also separate out what is the low frequency component and the wave frequency components? The idea is a little more general. So today we'll discuss more about the generic fixed gain observers, and if time permits, we'll come back and discuss that application to a heading autopilot today. If time doesn't permit, we'll do it tomorrow. Okay. All right. So one of the key aspects of when this fixed gain observer can work, where I can figure out what is the underlying state vector of the system, given that I know the control inputs and the measurements, is when the system is observable. So the idea, please understand here, that the system states are not all measured at all times. Many times we do not measure the complete state vector. For example, if you take a look at a full 6 degree of freedom model, then your complete state vector might have 3 accelerations, 3 angular velocities, 3 linear velocities, 3 Euler angles, and that can kind of already start to be, how many is that? 3 accelerations, 3 angular velocities, 3 linear velocities, 3 positions, and 3 Euler angles. 15? Right? So in a state vector which is 15 cross 1, I may be measuring only a few things. So for example, let's say I have a sensor as IMU. IMU is only measuring the accelerations and the angular velocity. So it's only measuring 6 quantities out of the 15 quantities. Right? So let us say I have a GPS sensor. GPS sensor is only measuring 2 quantities, the X and Y positions. That's all it is measuring out of the 15 quantities. Let us say now you have a LiDAR from which you're trying to figure out where your localization is. You may be able to figure out X, Y, and Z point of where you are, and probably an orientation angle as well, but it cannot give you velocities per se. If you have a DVL, Doppler velocity log, then you may be able to get velocity estimates out of it, but it will not give you position estimates. So please understand that each different sensor will be at any one time measuring a part of the state space. It will not be measuring the complete state space. So the question then becomes, do I have sufficient information to construct the complete state space at every time, based only on the measurements that I'm getting and the control inputs that I'm providing to the system, which in this case is rudder angle and propeller speed, for example. Right? Can I estimate the complete state vector? Do I know everything about the vehicle? And that can only be done when the system is observable. So we'll try to formalize this idea of when is a system observable. And this property is defined as observability. So the idea is simply how well can the internal states X of a system be inferred by only using the control inputs as well as the measurement outputs which I'm getting from the system within a finite time. Within a finite time, I need to be able to estimate it. I need to get a good convergence and be able to estimate it. So a system is observable if and only if, for any possible sequence of state and control vectors, the current state can be determined in a finite time, that being a very key aspect, using only the outputs of the system. If a system is not observable, then that means that from the measurements, some of the system states cannot be estimated. We do not know what their precise value is. So if I want to now pass this internal state vector to the feedback system, and I want to ask it to control it, what I can't estimate, I'll not be able to control as well. Okay, so as long as the system is not observable and you are asking the controller to control certain states which are not observable, you will land yourself in a problem. Okay, so you have to be careful about the fact that the system must be observable. So let us understand how to make this, how to evaluate the observability for a system. We'll start off with linear time invariant systems, which have a differential equation form as shown here. Okay. Why linear time invariant? What is the name's significance? These systems are linear in nature. These are linear differential equations, no non-linearity present. Okay. Time invariant in the sense that these matrices which you are seeing, A, B, C, and D, they are not varying with time. They are fixed matrices. Okay. That is why the name linear time invariant systems. Many of the systems that we experience, we will be seeing in engineering applications, will actually conform to this linear time invariant systems. Okay. A few times you will also see time varying systems, and we'll extend this applicability of observability, how to estimate or how to determine observability for those systems as well. But let's first discuss about time invariant systems. For a time invariant system, the observability can be determined from what is called as this observability matrix. So you can construct this matrix, which is basically a juxtaposition of different matrices together in order to form a bigger matrix. So I'm taking C transpose juxtaposed with A transpose times C transpose, A transpose square times C transpose, so on up till I have A transpose to the power n minus 1 times C transpose, where what is n? N is the number of states that I have. Okay, if my state vector is 15 cross 1, I have to do this for 15 times. So from C transpose, I will be going to A transpose to the power 14 times C transpose. Now, once I construct this big matrix, this need not be a square matrix. Okay, give me just 1 second. Sorry about that. Okay, where was I? So this matrix need not be a square matrix. Okay, in general, it will depend on the number of outputs I have and the number of inputs I have. Okay, if the number of inputs and outputs is if the number of output is 1, okay, number of outputs is 1, then C is basically a row vector. The output is 1, right? C must be a row vector. I'm just trying to understand that in this case, will it be a square matrix? So if it's a row vector whose transpose I'm taking, so this becomes a column vector, correct? And A transpose times C transpose will also be a column vector. Need not be. A transpose times C transpose will also be a column vector. That's right. Right? So all of these will be one column vectors. So then in that case, you will see this matrix turn out to be n cross n in that case. Right? Then it's a square matrix in that case. That's a special case. But in general, it need not be square. If you have multiple number of outputs, then you will see that, let's say I had 2 outputs. Then it will be n cross 2n. The number of columns will be 2 times n in that case. Are you following me? Is everybody with me? So it need not be in general a square matrix. Now, as long as this matrix has a column rank n, column rank of this matrix is n, which means it does not have more than n independent columns. The system is observable. Okay? So basically full column rank, as long as it has that, it is not, in that case, the system is not, the system is observable. So as long as the column rank is n, how come I did not write that? Oh, I did write it. Yeah, the observability matrix has a full column rank, and it, or at least has a left inverse exists. Okay, even if it doesn't have a column rank, can we find a left inverse for that matrix? And you can look up these definitions later on for a linear algebra perspective. Okay, what is a left inverse of a matrix? You can look it up. But for our purposes, generally, as long as we can see that the system has a full rank, then the system is observable, and in that case, all the states of the internal states of the system can be precisely estimated. Okay, as long as the observability matrix has a full rank, we know that we can get all the states of the system to be estimated, which can then be passed back to our feedback system. Now, in the case where we do have a linear time varying system, in which case A and C are actually now varying with time, we can, the observability will have to be tweaked a little bit. The definition has to be tweaked a little bit because now time dependence has come into the picture. And then the idea there is that you will have to formulate this so-called Graph matrix W, okay, and you have to ensure that this matrix is non-singular. Where this matrix phi, which you are seeing in here, is known as the state transition matrix. And what it means is that it is the states of the transition. So if I multiply this phi, t comma tau, with the state of the matrix at time tau, I'll get the output as the state at time t. Okay. The state transition matrix is basically a solution of the system of sorts. So if I know the solution at some time tau, in the future time where t is greater than tau, I can get the value of the state matrix by multiplying the state transition matrix multiplied by the state vector. You can actually show that this state transition matrix phi is equal to some u times u inverse, I think, if I'm not wrong, or u inverse times u. Let me just check that. State transition matrix is u times u inverse, correct. Where this u matrix, okay, so it is given as u times u inverse, where u is basically nothing but a matrix of a solution of u dot is equal to a times u, with the initial condition where u is chosen as an identity matrix at time 0. Okay, which means that if I chose u of time tau is equal to identity matrix, and I try to evaluate what will be u of t by solving it, which means that I'm basically taking one state at a time and seeing if I go forward in time, what is the solution I get. And I formulate that matrix as u matrix, u times u inverse is giving me the state transition matrix. Now, I'm not going to go into the details of all of this because for most of our applications, we will not be looking at so much time varying problems. We'll be mostly be interested in time invariant problems. But for the sake of completeness, I'm mentioning this. You can take a look at it at a later point of time if you are more interested in it. But please understand that even if we have a linear time varying systems, the observability concepts do apply in that case. But then you have to understand that a time limitation comes into the picture. Is it observable in a finite time t0 can be estimated by figuring out, formulating this matrix between time t0 to t1 and seeing whether this matrix is singular or not. Okay, is everybody following me? Yes, no, maybe. Yes.
So that phi matrix, it is a product of u and u inverse.
It's a product of u and u inverse.
Sir, won't it be just an identity matrix?
No. So this is what is the value of u at time t. You're solving for this differential equation by giving an initial condition of it being an identity matrix. So if at time t equal to 0, I have an identity matrix. I want to see at some time forward, how does u evolve? that value of u at forward time times its inverse is state transition matrix. So u is not identity there.
What is U, sir? Like, basically.
U is just a matrix. Okay, let me see. Okay, so let us say that I have my system x dot is equal to a times x, right? The simplest of the case, where I do not have a control input, nothing is being done else, right? In this case, I'm simply saying that if I have x, in one case I'll simply choose as 1, 0, 0, 0, 0, so on, and see what will be x of t. If x of 0 at time 0 is given by this, what is x of t? Okay, I'm finding out what is the value of x of t by solving this differential equation forward in time. Okay, and then I put that column into a bigger matrix here. Let us say, okay. Next, I go back and now I change the initial condition to be 0, 1, 0, 0, 0. Again, find out what is the new state vector which I get. Okay, and then I bring it and put it as the second column in my matrix. I repeat this until I shift that one from the top to the bottom of the state vector. Okay, so then what I'll get, I'll basically get n columns here, assuming that the state is belonging to real n. This matrix will be n cross n. That matrix is my U matrix. This need not be identity. In fact, will never be identity because it evolves forward in time. Okay, so now I take this U matrix, multiply it by its inverse. That gives me the so-called state transition matrix. Okay, this state transition matrix and the C matrix, the output matrix, now I can compute what is the observability matrix for that using these two values, using this expression. So once I have phi, I can compute this.
Sir, but a matrix times its inverse will always be identity.
Sorry?
U times U inverse will be identity matrix.
U times?
U inverse.
Oh, no. Okay, all right. I think you didn't understand this one. So this is U of t times U inverse of tau. So they are not at the same time. Okay, because I want to look at this transition from time tau to time t. That is what is my interest, right? If I move from some time tau to some time t, what is the state transition matrix? If ideally I want to start at time t and end at again time t, definitely this should be an identity matrix, isn't it?
Yes.
Okay, so and which is true in this case, right? If tau is equal to t, then this will become an identity matrix. Everybody with me so far? All right. So once I know that phi matrix, I can formulate this matrix and then figure out what is the so-called observability matrix. And if this matrix is not singular, then I can show that the system is again observable in the case of a linear time varying systems. Okay, all right. It's only mathematics which I am skipping over here because our interest is not in the mathematics per se, our interest is in the application aspect of it. All right, the same thing can be extended to discrete time systems as well. So many times what happens, we are not dealing in continuous time. For example, let's say that you're solving it using Runge-Kutta method. You're performing a simulation in your system. You're actually solving for the system at discrete time steps, isn't it? So in which case, we need to make sure that the discrete time system can also be observable or not. Because when and this is a whole new different field. Okay, I'm only including this for the sake of completeness. We will not be particularly using this directly. But discrete time systems are a whole new thing. So even though your continuous time systems may behave one way, but because I discretize the system, the dynamics may change slightly. So for example, depending on if I had x dot is equal to ax, okay? And if I used a forward time, x of t plus delta t minus x of t divided by delta t is a times x, then x of t plus delta t will be basically given by x of t plus a times delta t times, I can quickly on 1 plus this times x of t. Now, if I chose a different discretization scheme, say suppose I chose Euler's backward scheme, you'll see that that plus sign becomes a minus sign then. Right? And then you're actually looking at a slightly different problem. And you're actually looking at 1 time step behind rather than 1 time step forward. So this discretization will have an effect. So you see, although the original system was given as x dot is equal to a times x, the discrete time system's a is not the same. If I call this AD, then AD is 1 plus a times delta t. When I use it, Euler's forward scheme. But suppose I approximate the derivative in a slightly different way. If I take a higher order derivative, more central differences, more finite differences I choose, then it will change the fact what my AD value is, right? Even though all the systems are trying to only approximate x dot is equal to a times x, the continuous time system is the same. The discrete version may be different depending on the discretization that I use. Everybody with me so far? So therefore, it is important many a times that when we are dealing with discrete times, the discrete time system itself should be observable as well. Because of the degradation in the fact that I'm moving from a continuous time to discrete time, I should not lose observability due to the fact that the discrete system is not observable. So many a times we have to verify that the discrete system itself is also observable. So for that, we are talking about it when I said we are talking about it for completeness purposes, that's what I mean. Okay, and we are not considering discrete time systems explicitly in our in our consideration in this particular course. We have not dealt with it in a very detailed manner, and that's a whole subject in itself. But we'll see that it does come into picture when we are looking at Kalman filters and we are looking at application of Kalman filters. You generally tend to apply them in the discrete time because your measurements are coming at discrete times. They're not continuous. They're not analog signals. They're digital signals, which means you're getting those values at some discrete time. That is why you have a sampling rate for your sensors. When you say that my IMU is measuring samples at 200 Hertz, it's coming 200 times per second. Discrete values are coming at that rate. When I say my GPS is coming at 4 Hertz, it means that every 1/4 of a second, I'm getting a GPS input, I'm getting it. So that those discrete time aspects become important when we are implementing Kalman filters. From a control point of view, as long as the time step is too small, we are not too worried about this discretization making a big dent. But generally, when we are implementing it for sensor fusion and things, we are always implementing it in a discrete time sense. We're not implementing it in a continuous time sense. So therefore, for that completeness, we need to have the discussion about the observability in discrete time systems. So the same process follows, but it's slightly different. So a pair matrix AD and CD is called observable if and only if the unique solution of this matrix equation, where you're trying to solve for this matrix in WD, is positive definite, and its solution is usually given by this. So if this matrix WD is a positive definite matrix, then you know that the system is observable in a discrete time sense. Okay. All right. We are not going to be going too much into what degradation will happen when we are converting from a continuous time to a discrete time systems. That discussion we'll not be having in this course. But if you are really interested, I can point you to some material to talk about it. But I think it will just overwhelm the content of this course. So it will be beyond the scope of this particular course at least. Okay, all right. That being said, we will now come back to the idea. So we have discussed this idea of observability. Now, assuming that a system is observable, how do I design the so-called state estimators which can separate out my low frequency and wave frequency components? Let's try to take a look at it, and we'll try to apply this to the so-called autopilot systems for our ships. Okay, and so that it will become a little more clear. These observers, the simplest form of the observer which we'll be first talking about is called a Lewinberger Observer, and these have been in existence for a long time, and they're very traditionally used, so it's good to have a sense of understanding of what is going on. This will slowly build us into the Kalman filters as well. Okay, so think of it as a precursor before we go into the Kalman filters. All right. Okay, so let's see this. These observers are traditionally derived using a deterministic models, okay, which means that we are assuming that the dynamics of the system is pretty deterministic, which means I don't have any noise, I don't have any process noise, I don't have any measurement noise. We are assuming all of that when we are deriving these state estimators based on Lewinberger Observer. But we can still apply it even when some noise does exist. It is robust enough to take care of them as long as the gains are tuned a little bit properly. And we'll talk about what those gains are and how do we make sure that this works. And you'll see that those who have taken maneuvering course with me, you have seen this before. You probably have not looked at the name as this, but you have looked at it under the name of state estimators. Okay, so if we have a typical LTI system, linear time invariant system, which is given as this, where X is my state vector and Y is the output which I am trying to measure, then the observer is simply following the same dynamics as my plant. You will see that it is similar, X dot hat. So I'm representing my estimated state as X hat, and I'm differentiating that from my actual state X. So I do not know the actual state. I only know I'm trying to get the best estimate of my X hat from my measurements Y. Okay. So the idea is that I know what is Y. These are measured. Similarly, I know what is U. So these are control inputs. But I do not exactly know X, at least not precisely. Okay, I make my best estimate of X and I call that as X hat. So X hat is my best estimate of what I think X might be. Okay, so even though I do not know X and I only know X hat, I want to ensure that my X hat is approaching X. As long as I can mathematically prove that X hat approaches X, I am fairly confident that whatever I'm getting out will be close to at least the real states that I am interested in. So I define my so-called observer as X hat dot, which follows a similar dynamics, A times X hat plus B times U plus K times Y minus Y hat. Where what is this Y hat? This Y hat is the so-called measurement I would have got had the state been X hat. So if my state was actually X hat, what is the measurement I would have got? That would be Y hat. and then I'm trying to see that what is the actual measurement I got versus what should have been coming. And if the two are same, then I know that the filter is working properly. Okay, in the aspect that the filter is working correctly, this term will come out to be 0, right? Y minus y hat, y tilde and y hat should become 0 if the filter is approximating the states correctly. Is that making sense?
Yes, sir.
Yes, Aditya.
What is the difference between this y and y hat?
Y is what we measure. Y is the measurement.
Y will be our sensor data.
Yes. Okay. Y will be our measurement. Based on this measurement, I evaluate what might be the best estimate of my state, x hat. Okay.
Yes.
That best estimate of the state, if it were true, if this were the actual state, then what should be the output that I should have seen will be y hat. Based on the fact that I know some modeling of my system, I know some parameters of what dynamics it is following. If x hat was the real state indeed, what should I have measured according to my model?
Okay.
Okay, that is y hat. Now, as long as y hat and y are approaching to 0 or approaching each other, the difference will go to 0. Okay.
Yes.
In that case, my estimator's dynamics is exactly the same as my original system's dynamics. Isn't it? This, which you see here, this term will go to 0. This entire term will go to 0, and I'll have x hat dot is equal to a times x hat dot x hat plus b times u, which is the same dynamics as what I have for my real system, right?
Yes.
In the reality is we do not know what the actual system might be looking like. There might be some other things which might be happening in the real thing, which we may not be aware about. There may be some dynamics which we may not be capturing properly. So that is why we are trying to make sure that this error should be driven to 0 as much as possible. Is that making sense? Yes, no?
So we are giving output as feedback for this group.
Correct. Yes. So for this observer, the sensor information is being fed into it as a feedback mechanism to correct its internal states. You can think of it like that. That's right. Okay. All right. Now, this matrix K which you see here, that is called as the observer gain matrix. And that is the gain matrix that we tune. We decide how big of an effect should that error have. If the unmodeled dynamics is huge, if there's a lot of unmodeled dynamics which I'm not capturing in my dynamics, then I might want to take a bigger value of the gain so as to incorporate that effects into my state estimation. Okay, so this gain will determine how fast the convergence actually happens. Now you can observe one thing. If I define this so-called estimation error as x tilde as x minus x hat, then the error dynamics, okay, so I can simply take a difference between this equation and this equation. Okay, do it and see what do you get. On the left hand side, I will have x dot minus x hat dot, correct? Yes, no?
Yes.
That is nothing but x tilde dot, right? Because the difference is what I have defined as this x tilde. Now on the right hand side, when I take the difference, what will I get? A times x minus a times x hat. That is nothing but a times x tilde. B of u and b times u will cancel out. Okay, what am I left with? I'm left with this term, k times y minus y tilde. That is nothing but minus of k times Y itself is C times X plus D times U. And Y hat is C times X hat plus D times U. So D times U gets cancelled out when I take the difference, right? And what I'll be left with will be C times X tilde. So I can kind of write this as K times C times X tilde. So in essence, this becomes a big matrix A minus K C times X tilde. Is everybody with me so far? Now you can see that as long as the eigenvalues of this matrix are real and negative, or have a real and a negative component, then this error will go down to 0 over time. Everybody with me so far? Shadab, with me?
So when is the error will be 0, sir?
The error will go down to 0 as long as this fellow's eigenvalues have negative real parts.
Negative real.
All eigenvalues have negative real parts. So as long as that is the case, this will go down to 0.
So is this something kind of a property of
It is an exponential property, right? If suppose in the scalar case, if let's say x is scalar, x dot is equal to a times x, the system's response is x is equal to e to the power minus at, right? This will solve the system basically.
yes, sir.
E to the power at basically, sorry.
Sir? Sir, is it like a Hurwitz matrix?
Yeah, Hurwitz matrix is slightly different to my knowledge. The matrix is Hurwitz, then it's invertible also. Yeah, you can, yeah, that is right. The matrix is Hurwitz, that's right. The matrix is Hurwitz means all its eigenvalues are negative real. At least their eigenvalues have negative real parts.
So this is like asymptotically stable.
Then yes, the system, the error basically is asymptotically stable or decaying back to 0. So no matter where I perturb it and I let it go, the error will come down to 0.
Yes, sir.
And that basically means that my state starts becoming equal to my estimated state matches with my real state. Even though I do not know my real state, I can guarantee that my estimated state will start tracking my state. Okay, that is the beauty of the process. I don't know the error with respect to which this is going to 0, but I can be sure that the error will go to 0. Okay, that is the fun part of this. Okay, and notice that asymptotic convergence of x to 0 can be obtained from a constant value of k if then this is only possible as long as A and C is observable. So if the observability property does not exist, you cannot prove asymptotic convergence. Only when the system is observable, all of this holds true. Okay, we'll stop here for today and recontinue tomorrow, where we'll see the application of this observer for our heading autopilot, where we'll try to look at our ship's simple Nomothos model, where we'll assume that we have a compass which is measuring both wave frequencies as well as low frequency stuff, but we want to isolate that in order to get the low frequency component separated out. How do we get it from a Lewinberger observer? How can we build an observer to make that happen? Okay, and we'll see that whether that system is observable or not. Okay, so that will be all for today, unless there are any questions. Are there any questions before I close off? No questions? So let me stop recording.